Hi, I'm Yongjie Wang, a third-year PhD student in Nanyang Technological University. It's my great honor to introduce my research work, DualCF, Efficient Model Extraction Attack from Counterfactual Explanations. Our paper aims to extract a cloud model from counterfactual explanations. Here I introduce model extraction attack and counterfactual explanations briefly. Model extraction attack aims to obtain functional equivalent or near equivalent machine learning model, which achieves high agreement as a class model with as few queries as possible. Counterfactual explanations answer what minimal changes are needed for an input instance to alter the current prediction to a particular different one. Counterfactual explanation methods can be bidirectional and capable of flipping prediction of any input. For example, counterfactual explanations from a desirable prediction to undesirable prediction indicate the actions we should avoid. A recent study forcibly conducts model extraction attack on counterfactual explanations. By considering these closed boundary explanations as additional training instances. But this method suffers decision boundary shift issue. That is, the decision boundary of the substituted model shifts away from the decision boundary of the cloud model. Here we introduce where this issue comes from. To minimize the core entropy loss in classification, the cloud model tends to assign a higher probability on actual class. So the probability density counterlines become denser during training. We can see this phenomenon from these figures. Input instances are randomly sampled and can be far from decision boundary of cloud model, whereas counterfactual explanations are close to decision boundary of cloud model. To separate these points confidently during attack, substituted model tends to move towards the middle area between inputs and counterfactual explanations, which shifts far away the ground truth. To mitigate this problem, we should find proper queries with similar distance to decision boundary of cloud model. Directly selecting these queries are difficult because we have no information of decision boundary in the beginning. Our method leverages the counterfactual explanation API to achieve this. Our method first feeds a query X into API and obtain a counterfactual explanation denoted by C. Then feeds a current counterfactual explanation C into the API again, obtain a counterfactual explanation of C denoted by C prime. Because C and C prime are counterfactual explanations produced by the same interface, they are both close to the decision boundary of cloud model, but with different predictions. Here's our algorithm. The G is a counterfactual explanation API, which takes a prediction model F and a query as input and produces a counterfactual explanation. Line 5 obtain an explanation of a query X. Line 6 obtain an explanation of C. Then we merge pairs of C, C prime, and their predictions to form the dataset for substituted model training. We also consider a variant of our DualCF, which takes original training data as well. We named DualCF-X. Here we use a toy example to compare existing work and ours. The figure A and B show that substituted model decision boundary shifts away from cloud model's decision boundary. Therefore, existing method had to consider more queries to achieve high agreement as a higher attack cost. Our method considers CF and CCF intertraining achieves comparable agreement with fewer queries. We consider the following baselines. The first two methods only use prediction information, different in how to select queries. The third method treats counterfactual explanation as actual training data. We evaluate our method on 2 synthetic datasets and 3 real-life datasets. The evaluation matrix consists of mean and standard deviation of agreements of 100 random trios. From experiment results, we can see our method can achieve better agreement when query sets are small. The gap decreases when query set becomes larger. From the bottom figures, we can see our method is less sensitive to initializations and samplings. Here are my future work and references. Thanks for listening.